Hey guys, welcome to the second part of my video on how to design a 3 GHz low noise amplifier. For the first video that I designed the schematic layout of the whole thing, the um, the basic principles on how to design your stub matching networks for the input and output of the low noise amplifier, and also stability resistors and reflection coefficients to design the best optimum reflection, the best optimum source reflection coefficient to use for the best noise figure for your amplifier. So if you want to learn more about that, go back to my other video on the first one, and then you can learn more about what I'm going to be doing in this next video. This next video I'm going to make the whole PCB layout, and the layout is going to be more detailed. It'll show exactly how the pads on each of the on every component is. For example, like the inductor, the DC block capacitors, the resistors, they all have pins that have specified dimensions on them, and you need to figure out what those dimensions are, and those would be the pads for your PCB layout, and also including the PCB pads for the transistor itself. But I'm not going to specify all the pads for it. You can go ahead and look at the data sheet here, and there's also the pads for it. You got the exact dimensions of them. You're going to have to do this yourself, but my dimensions are not going to be the same, and I'm not going to include DC block capacitors, DC feed inductors. I'm not going to include those because they're not from specific manufacturers. They're just ideal circuit components. But if you're going to make if you're going to make specific components, then those are going to have to make sure you include those pads with it. So what I'm going to do now, the first step is to go to layout, go to generate update layout, click OK, and now as you see here, you have a bunch of lines here, and that means that the transistor does not have specified pad parameters for the transistor itself at all. So we're going to delete that because it has nothing to do with it, and I'm not going to use any DC pads for the blocks or feed capacitors, DC block capacitors and DC feed inductors. I'm not going to use them. And plus, as you can see, they have X's in them, meaning they do not have specified pads at all. So we're going to delete those. We're going to delete the whole thing and the grounds. And with the grounds, we're just going to go ahead and put put in vias, put in our own vias that we define on the layout itself. So as you can see, when we generated a via, we had one right here, but I'm going to generate one on the layout instead. And as you see here, this is grounded, and this is also going to go to a via also. The vias will go from the top layer to the bottom layer, and the bottom layer is the ground. So here is the output here. This is where the drain is, and then this is the stub. As we can look at the schematic here, this is 191 mils, and the straight area right here is 80 mils, 80.5 mils right here. So we want to make sure that everything is in the correct dimensions, especially if you're going to design this exactly the same way as if you're going to design this on, like, be very specific with how your design is. Yeah, you're going to have to be very specific with your design when you design a low noise amplifier. So just keep that in mind. So as I told you, I'm not going to include the pads. So what we have is we just have the drain coming in. We have a DC block that will come after it, but I'm going to include those when I create this thing and I put this into the schematic, but I'll show you that a lot later on. Just hold on and I'll show you what I'm going to be doing more. So these pads, I'm going to make a source pad now, but as you can see here, I cannot get the same dimension as over here. It skips the dimensions of this transmission line. And in order to get very better precision of the transmission line here, let's go to options, grid spacing in here. Now we can go anywhere we want. So we go here. There. And now we can copy this. So as I told you, I am not going to specify the dimensions of the pads. The dimensions are totally different actually for the different sources here. For source 1 and source 2 are totally different dimensions. But I'm just doing this just for the simplicity of the video. So next step, we're going to insert the pins, specify what pins are going to where. So this is where the drain is here. So D, we'll put D for drain. But actually that's where the capacitor, the DC block capacitor is going to be coming out of. But then also the DC block capacitor will be going into the drain also. So we're just basically specifying the pins and what's going to where. So alright, so pin 2 is S1. We're going to rotate this, put the pin as close as we can in the middle here. And this will be the drain, which will be pin 3. And you can get those, let's see here. Oh, you know what? This is actually supposed to be the gate, G. I didn't see that. And this is going to have to be D, the drain. And then this is the other source, S2, which is pin 4. I don't think the pins really matter, but I'm doing it the same orientation as what the what the data sheet would have. The data sheet has the pins in the same order here. So 1, 2, 3, 4. So now I'm going to find our ports. So this is going to be port 1, P1 here, and that's going to come from the input of the 50 ohm termination. Port 2, rotate this, and that's going to go to the output 50 ohm termination. Now the next step is to define the ground plane, and the ground plane is going to be a different layer. The layer is the same layer as the transmission line. Is not what we want, so we want to make sure that this is separate. It's going to be a different conductor, so we'll call this con 2 and press enter, and this becomes green. So the next step, we have we need to have a substrate between the conductor and between the transmission line and the ground, and that's where we need to come in and make a substrate. We go to substrate editor here. But one thing I forgot here actually is we need to specify that the ground plane is a ground. And I've noticed that this is a big deal because it will mess up my simulation if I don't make sure that this is specifically the ground. So there's a code that I put in as GND exclamation point, and then press OK, and this actually creates that this is a ground actually. Because if I don't have it there, I don't know, I've noticed it doesn't work when I put this into the schematic. So if you guys have another way of doing this, that would be nice. But this is the only way that works for me right now. So I'm also going to specify another ground, which will be closer to the drain. So I'm going to put a ground there, and then and then after that we're done. So the next step is to make the substrate, and that's going to be between the transmission line and the ground. So there's no substrate. Click OK, And there's many substrates here. You can use FR4 board all the way up to calcium arsenide, but I'm going to use alumina substrate, 25 mil. So as you see, there is a cover. Using a cover, I think you can use that as a ground plane, but just to be safe, I'm going to delete it. I'm going to specify this as air here because think about it, if I'm going to test this on a VNA, then you know what's going to be between my printed circuit board. It's going to be air here and air at the bottom if it's dangling up in the air, you know. So I'm going to go ahead, I'm going to map a conductor layer for the ground, and the ground, what we already specified was con 2, and the thickness was 0.15. Now the conductor layer for the transmission line is 0. And the thickness of that is 0.15 mils. And the dielectric is 0.15. I mean 25 mil. There you go. Now, one more thing, we need to map a via. There's many different types of vias here. You got a semiconductor via, dielectric via, all of these. These could be used, for example, like on a chip design, maybe, you know. You would design like a low noise amplifier chip, but mine's not a chip, it's PCB. So the thing is that I'm going to, what I'm trying to do really is just conduct the transmission line to the ground. That's all. So I'm going to map the conductor here, and I'm going to call it default 0 here. And then that's it. Just press save, exit out of it, and then we could click on via so we can map it via to, so you can see here it says that there's no via definitions available, so we need to create a via definition. So we go to options, technology, via definitions. Now you go to add, and we specify the diameter, which was actually 40 on the schematic, but I'm going to go put 30 because 30 is about the same, almost the same length as the transmission line. It's really big when you put the 40 in there. So, and this is the hole size, 20 mil. And the width of the transmission line is 24 mil, right? So, click OK, close. Now let's see what happens when we click on via. And now it says actually what we need to do is that there's no tech substrate. We need to define a tech substrate. In order to do that, we go back here, we go to substrate here, and I don't know why, it's kind of weird. We have to rename it as tech. Now click enter, and then you have to click on it again just to refresh it. Click OK, and then maybe save again. if you want. And then now we can map a via, finally. Now there's different settings that you can have. You can have through, but the best one, I don't know what through is, what specified drill layer is, but when it's between top and bottom layers, I know that the via is going to be between the top and bottom layer, so that's what a via is supposed to do, is connect the grounds. So as you see, there is now a ground on the via, which means that it connected straight to the ground, which is what we want. And that's why I put that code in over here as ground over here. So GND exclamation point right there, and it defined the ground. If I did not put that down, then this would not have a ground right here. And that's what's nice about it, because I have a ground here. Now, or I can go to actually insert via. There. Now, on the schematic, it actually showed you that there were two vias right next to each other. You could put one right next to each other, maybe put this one down a little bit and then this one up. And then you have two vias back to back right next to each other, which would increase the performance of your low noise amplifier. It would make sure it would be less prone to losses. So that's what I've read and heard. So you could also do two vias at the shorted stub, but I'm just going to use one for now. Just for the video. There you go. And then I think I'm done. That's it. So next step is to create an EM simulation. Click on EM and create EM setup. Click OK. Now there might be warnings here, and you want to make sure that there's no warnings, or else you're not going to be able to simulate it. Go to adaptive, linear, click on step, and simulate. Now this could take a minute, but just you could fast forward the video and see me on the next slide of the video, but I'm going to have this thing run till it's done. And it is about finished. Alright, now, next step, what we do is we exit out of here, click no, and we don't have to save any of this. One other thing I did not get to show you is before we started simulating this, we could go to 3D print, not 3D print, but look at the 3D view of the layout here, and that you can use that to figure out, make sure that everything is in place to where you want it. So this might take a minute. Just wait for a second. You can also use this layout, 3D layout, to look at the EM simulation for the for your low noise amplifier circuit. But I'm going to make this very simple and going to exit out of it and just do this simply the way that I'm doing it now. So the next step, we need to create an EM model and symbol. So we go to component, create EM model and symbol, and this will go onto your schematic. Click OK, and then go back into your schematic here. You don't need to have this anymore. You actually really don't need to have these. You don't need your transmission lines anymore. You don't need your M sub. You don't need your vias here because you already have vias at your sources. And instead of having to delete them, you can also delete the whole schematic, but I am just going to delete the pieces anyway. But we need to have the 50 ohm terminations because we have our port 1, port 2. We need our batteries, we need all these components in there. But the thing is, we do not have the pads that go in between our capacitors because they weren't specified, and these are just ideal components. They don't have any manufacturer where they come from. If you look for a DC block capacitor, you know they're going to be a really high value capacitor than what the frequency would want. So usually maybe like I'm guessing a little bit more than picofarads, like nanofarads, or maybe a little bit higher than nanofarads for a DC block. but you're going to look at those capacitors and on the data sheets and use those pads in between each other. But for me, I don't have any pads for it, so I'm just going to use the ideal circuits here, and I'm just going to use the ideal resistor here for 300 ohms and 200 ohms over here. And you can also include the DC bias network, but I did not include the DC bias network, where you can just use one battery and you have 0.5238 volts coming in to the gate, and you have 3 volts here. But I'm not going to do that. So the next step, what we need to do is go to libraries, go to workspace, libraries, cell 1, and now what you see here is the layout. And that layout has the pins here. So here's your source 2. S2 is going to go here. Everything is going to look like a mess actually, but you can also make things everything on the board exactly how it's supposed to be. Everything is outside, but don't worry too much about that. Everything looks messed up, but you can figure out the pads for the components here and everything, and put all the components onto this layout here. But I'm just doing everything outside because it takes up too much space doing it the other way. So alright, and this will go to the gate. These are grounded here, as I specified. I put those pins there for ground. Now these are the 50 ohm terminations here. This is port 1. And then this is port 2. And everything is connected. Every pin is connected. So now we have our S parameter palette, and all we have to do now is simulate it and see what our S parameter response is. And one more thing I forgot to tell you, if we get this warning here, it means that we have not specified that. We need to make sure that our simulation is an EM model simulation. So in order to do that, you go to insert, or no, you go to edit, component, and choose view for simulation. Or wait, go to edit, component, choose view for simulation. Okay. Alright. Go to EM model here, click OK, and then that should be it. That's because I clicked this area. You want to make sure that you click the layout, or else it's not going to work. You want to make sure you click the layout and then go to edit and then go to component and choose view for simulation and then click the EM model. So now click simulate, should go through now. Now let's see what our response looks like. As you can see, the response for 3 gigahertz is not really that great. We got a 12 dB 12 dB gain, and our return loss for the output is negative 9.6 dB, and the input return loss is negative 15 or 15 dB. So we can always improve this by maybe specifying a different dimensions for the transmission lines, or many other factors. We can specify a different reflection coefficient for it at the beginning of the design. When I designed it on the schematic, we can do that. Many other things, but I'm just going to go ahead and leave it for this now, and I hope you enjoyed my video, and please subscribe. Thank you. Bye.